Alright, so I have to try to remember to look for the red light being on, because that's how we're being recorded. And try to remember right over here, so that everything is visible to the viewers at home, so to speak. Let's see, log in. Alright. Let's get started, shall we? Who wants to begin? There we go. That was a nice touch. Presentations loaded. So, somebody can ask a question. No questions are great. Okay. Yes.
Just one, you have a number of questions, so.
All right.
But when you ask, like, why, how is gravity objects in orbit? Do you want like they're falling around the sun or whatever? Is that what you're looking for?
Yeah, they're falling around the sun, but in particular, what I want you to understand is this analogy between what keeps a ball in orbit if you're swinging it over your head. Well, it's the force from the string pulling inwards on the ball, right? What keeps the moon in orbit around the Earth? It's the force of gravity pulling inwards on the moon. What keeps planets in orbit around the sun? It's the force of the sun's gravity pulling inwards on the planet. So there's this analogy between the force of gravity that pulls on a ball to keep it moving around instead of flying off in a straight line. Same deal. Gravity's the string, if you will, that keeps the Earth from flying off in a straight line instead of orbiting the sun, and so on and so forth. That's really what I'm looking for there. All right, let's see. My password, which I recently updated, is ... This ain't going nowhere unless I win. Try this again. Next. But not with that password, you doofus. There we go. Okay. Oh my God. Plan B. Wire connection. Somebody can ask another question, maybe I can answer it without this. Yes?
Kind of going off of that, so in uniform circular motion, you asked where the acceleration vector is pointing. Is it pointing straight at the object that's being orbited?
In uniform circular motion, it is, but more fundamentally, it's pointing at the center of the circle. In uniform circular motion, the acceleration and the force both point towards the center of the circle. Okay. Which, if you're uniformly circularly orbiting the sun, says the force is pointing towards the sun, which we know because it's a force of gravity pulling in that's doing it. But that fundamentally, in uniform circular motion, the force and the acceleration both point towards the center of the circle. It is not tangent to the circle. The velocity is tangent to the circle. It's the velocity that's tangent to the circle. The acceleration is pointing towards the center of the circle. So the velocity and the acceleration are actually perpendicular to one another. other words, here's the circle, here is the object coming along, its velocity is along a tangent to the circle, and the acceleration 90 degrees away is pointing towards the center of the circle.
So that's why, like in the ball example, if the string snaps, it'll continue at constant velocity.
You know it, that's right. In the ball example, if the string snaps, no more force, then time for Newton's first law, no force means move in a straight line at constant speed, so it will fly off on a tangent to the circle.
Okay.
If it snaps, and you're doing it in space. I mean, on Earth, it falls to the ground because we got gravity from Earth here. But if you were swinging a ball around your head in outer space, which would be really cool if you could do that, if the string snapped, whoo, the ball just flies off in a straight line after that. Yes. So, okay. Now I will connect to Google Drive, slowly but surely. Okay, so, any further questions about that, or should we? Yes?
Can you explain the black body stuff again?
Uh-huh, okay. Where should I begin? At the beginning, right? So, that would be chapter 5 and stuff. So, a black body is a hypothetical perfect emitter and absorber of radiation. So, perfect absorber of radiation means that it never met a photon it didn't like. Any photon that touches the black body is munched by it. It just eats it. It's gone. So it absorbs absolutely all the radiation falling on it. That's not the whole story. It also emits a black body spectrum. It emits radiation as well at low temperatures, like say the temperature of the human body. Are you giving off visible photons? No, you're not. How come I can see you then? If you're not giving off light, why can I see you? Because you're reflecting light, right? Yeah. You're reflecting light. If I turn off all the lights, I won't be able to see you anymore because you're not emitting light. You're not giving off your own light, but you are reflecting light to me. So you're certainly not a black body because you're not absorbing 100% of the radiation that falls on you. That's a good thing. It would be hard for us to interact with one another if we didn't reflect any light towards one another. Are you giving off any electromagnetic radiation? You are, yes. What part of the spectrum is the radiation that you are emitting in? Infrared, yes. If we had infrared sensitive eyes, we'd see each other positively glowing. You'd literally see one another glowing. You could read your book by holding your hand up to it, just reading from the glow of your hand on the book. But your eyes are not sensitive to the infrared, so you don't notice that. You don't see it. And even if they were, well, you'd have a problem in that your eyes are at body temperature, so all you really see is just the glow of your own eyes. You'd have to cool them down in order to make this work. You'd have to refrigerate your eyes below body temperature in order to be able to use them to see one another. Okay, but anyway, be that as it may. So a black body absorbs all the radiation that falls on it, but it also emits radiation. The reason we call it a black body is at low temperatures, when it's not hot enough to give off visible light, then it would look perfectly black to our eyes. Crank up the temperature high enough, though, and it starts to give off visible light, in which case we would no longer be at all tempted to call it a black body anymore, and we'd use the more kind of generic term like thermal emitter or something like that. But the term black body is stuck. But it's really just what it would look like at low temperatures when it wasn't glowing with its own radiation that was giving off. So that's the black body, like basic definition. Do you want me to continue on and so what does the radiation look like? It's those curves and stuff like that. There's the radiation laws and all that sort of thing.
That would be good.
Okay, so let's do that then. And no, I don't want to connect to BishopNet because it's wired now, so. and Kelsey and Ryan are looking at it too. Okay, all right, very good. Let's go ahead and get to the radiation laws. Here we go. So a black body we say it's a perfect emitter, what we really mean is it gives off a spectrum having this specific shape. There's a mathematical function which describes how bright it is at every possible wavelength for whatever the temperature it has. We didn't write down the mathematical formula. It's a fairly complicated formula whose details are not so important to us. But it has a specific mathematically defined spectrum that only depends on its temperature. It doesn't depend on what it's made of. It only depends on the temperature of the black body. And in particular, when we had a light bulb that I started cranking up its temperature by increasing the voltage across it. So two things happened to the light when I cranked up the temperature of the light bulb filament. It got what? And it also got what else? It got brighter. It got brighter and brighter. That part shows up in the fact that, notice, 310 Kelvin human. We puny humans emit infrared light and not all that much of it. But take something at 3,000 Kelvin, and each square meter is giving off a lot more light than each square meter of us is. And by light here, I mean generally electromagnetic radiation, not just visible light. So 3,000 Kelvin star gives off this curve. So this is, each point on the curve is how much energy is coming out of each square meter of the surface every second. 3,000 Kelvin star, more energy coming out of each square meter at every wavelength. The sun, 5,800 Kelvin, even more energy at every wavelength. 15,000 Kelvin star, even more energy at every wavelength. The fact that as you raise the temperature, it gets brighter at every wavelength means that the light bulb got brighter and brighter as I cranked up the temperature. So visually, it means it just gets brighter and brighter as I crank up the temperature. And the other piece is, not only did the temperature, not only did it get brighter, it also did what else? It got hotter, right? But that's the, I won't disagree with that. But the temperature is the thing that's affecting the light. So what else happened to the light? Not only did the light get brighter, changed color. It changed color, right? It got whiter and whiter, right? Changed color. When I first got it to start glowing, it's kind of dull orange red. Hot coals are that color because they're warm enough to give off some red light. That's what makes hot coals have their color. A burner on a stove, when you get it warm enough, glows red for exactly the same reason. It's warm enough to start giving off some red light. But if you made it hotter and hotter, it would be like, if you start getting to molten steel, it starts looking orange and then yellow. And if you get it really hot, it looks white. Same kind of idea. Eventually, it would start looking bluish in color, but it would vaporize before it did that. So a star doesn't have to worry about that. Stars vapor anyway. So what property of these curves is reflecting the fact that the color is changing? The location of the what on these curves reflects the color change. The peak wavelength. The peak wavelength, right? For the 310 Kelvin human, the peak wavelength is way over here at about 10,000 nanometers. In the Mastering Astronomy homework, you discovered that it was 9,470, I think, nanometers at some point for that. Did I give you that as that problem where you calculated that, or is that something? Oh, never mind. That's a different class. Okay, different class. That was Astronomy 260. Kidding. Okay. Humans give off wavelengths most strongly at about 10,000 nanometers, 1/100 of a millimeter, in other words. But a 3,000 Kelvin star, its peak is over at this wavelength, so on the order of 1,000 or so nanometers. Is that a visible wavelength? Is this wavelength visible to humans? No, because we can see from where to where wavelength rise.
Over 400 to 700.
About 400 to 700, yeah, 400 to 700. The peak of the 3,000 Kelvin star is in the what part of the spectrum? Infrared, just like humans, but it's in what we call the near infrared as opposed to the far infrared. Far infrared meaning much longer wavelengths than visible. So we humans emit at far infrared wavelengths. A light bulb filament emits mostly at near infrared wavelengths, but there is visible light. It doesn't emit most strongly in the visible, but it is giving off visible light. More red visible light than blue visible light, or in general more long wavelengths of visible light than short wavelengths of visible light. So the light bulb looks reddish in color when its temperature isn't very hot yet. And similarly, a lowish temperature star looks reddish in color to our eyes, like Betelgeuse, for example, or Antares, red supergiants. Crank up the temperature for the sun, it actually peaks in the visible part of the spectrum, which is why our eyes are most sensitive to that part of the electromagnetic spectrum, because our eyes evolved to be able to see the light that our star gives off, so that we don't get eaten and all that sort of thing. And we can find food and all that good stuff. Raise the temperature further still, really high temperature, 15,000 Kelvin star, the peak. Is this peak wavelength visible to us? No. What is it?
Ultraviolet.
Ultraviolet. It's not visible to us. But that doesn't mean the star isn't giving off light visible to us. It still is, but now notice the slope is such that it's giving off more short wavelengths of the visible part of the spectrum than long wavelengths. So that star looks bluish to our eyes, because now the balance is it's giving off more blue light than red light. So it looks bluish to our eyes. Yes?
So are most stars blue and red?
They actually span the largest number of stars in the universe. About 90% of them are what are called red dwarfs. So most of the stars in the universe are actually dim red stars. There are a lot of really bright blue stars in the universe, but they are spectacularly bright compared to other stars. So when we look at a galaxy like the Milky Way from the outside, they look blue. It's not because most of the stars are blue. It's that a single blue star can outshine like a million suns. So even though there's not a lot of them, it's like you're in an audience and most of the people are whispering, but there's that one jerk who's saying, "I need to check my phone!" And so everyone notices the jerk, even though most people are much quieter. Galaxy's kind of the same way. Most stars are much quieter and meeker, but we have these hot young blue stars that are really obnoxious, that give off lots of light, and they dominate the light that we get. But it turns out the sun is more massive than 90% of the stars in the universe. The sun's actually a big star. We're often told, the sun is so. There are stars much bigger than the sun, but the sun's more massive than 90% of the stars in the universe. It's pretty big as stars go in the end. Yes?
At some point, can you please discuss ionization of the
We sure can. Yes, we sure can. Yes. Did you have a...
I had a question related to this.
Yes.
So, if we added dips into this
Spectra.
so then that would talk about their spectrum.
Yeah, so the thing is that these are black body spectra. Real stars' spectra are not black body spectra. They're just rough approximations to a black body spectrum. A black body spectrum is a continuous spectrum. We know that real stars have absorption lines. So, in other words, a real star spectrum, this is just a first approximation to what it looks like. The details are different for a real star versus a theoretical, hypothetical, perfect black body.
So these are saying that if it's completely straight and nicely curved and no breaks, that means it's a perfect black body.
Then it would be a perfect black body. Yeah, perfect black body would be this nice smooth curve, no dips, no bumps, just this nice smooth curve. But the only way to get that to happen is for the entire star to be at the same temperature, but that doesn't happen. Stars are hotter in the middle than they are on the surface, and so that leads to the differences, basically. Yep. Any more questions about black body kind of stuff? Yes?
So this is just like a theory about like how a perfect star should operate?
Yeah, it's not so much just like a perfect star. So thermal equilibrium is the technical term that physicists use to describe something that has every part of it at exactly the same temperature. If you could construct something that had every part of it at exactly the same temperature, then you could get a perfect black body spectrum. But you can never actually make something that perfectly have the same temperature everywhere inside of it. So real stars, or real people, or real things in general never give off perfect black body radiation It's an ideal that's approached as you make something more and more uniform in temperature and so forth throughout it. But you never actually get there for the real world. Okay. Any other questions about hot coffee? All right. Can we please get to ionization, did you say? Yes, okay. So next topic, ionization. Like, can you be more specific, or are you just like, ionization, discuss?
There was a question that said, like, define ionization, and I know what the definition is, I just need, I guess, a good example.
Yeah, so ionization means the removal of electrons.
Yes.
Yep. So if an atom, I don't even know if I have a picture of that. If an atom is missing, oh, it's kind of here. If an atom is missing electrons, it's an ion. So hydrogen, an ordinary hydrogen atom has how many electrons orbiting it? Anybody know? One. Yeah, it's actually one. Hydrogen is the simplest element. It has one proton in the nucleus orbited by one electron. And we know that electron has energy levels. It has a lowest possible energy. What do we call the lowest possible energy? The ground state, right? Lowest possible energy is the ground state. Then there's, so the ground state, your book calls it level 1. Level 2 is the next higher energy up. Level 3 beyond that, and so on and so forth. If you give the electron enough energy, it's free to fly away from the nucleus and never come back again. That's ionizing. So so how much energy does it take to take an electron from the ground state to being ionized? The answer is 13.6 electron volts. So if a photon comes along and it finds an innocent hydrogen atom with its electron in the ground state, and that photon has 17 electron volts of energy, that photon can kick the electron out of the atom, and the extra leftover energy will give it some energy of motion after it flies out of the atom. And that's the idea of ionization, is energetic enough photons can kick electrons out of atoms. It's not the only way to do it. Rapidly moving atoms colliding with one another can do it too. So violent collisions, sufficiently energetic collisions, and sufficiently energetic photons can both strip electrons off of atoms, and we call that ionization. That's the idea of ionization. Yes? Yeah.
Going on with that, I know what the definition for an isotope is. However, when I see a list in a quiz, my mind just goes.
Okay, if you want isotope, what you want to do is zero in on this.
Okay.
If let's see if I've got a picture here. If you have, maybe not, but it doesn't matter. If you have isotopes of the same element, so it's the number of protons that determine what kind of atom something is. Every carbon atom has 6, count them 6, exactly 6 protons in the nucleus. If it ain't got 6 protons, it ain't carbon. But the number of neutrons can differ. So there is an isotope of carbon called carbon-12, which has 6 protons and 6 neutrons. 6 plus 6 is 12. There is an isotope of carbon called carbon-13. How many protons does carbon-13 have? 6, because if it ain't 6, it ain't carbon. Okay? So every carbon atom has 6 protons. The number of neutrons is what differs. So carbon-13 has 6 protons, but 7 neutrons. And it's called carbon-13 because the total number of particles in the nucleus, the protons plus the neutrons, is 13. 6 protons, 6 neutrons. So if you're confronted with, here's a list of stuff, which ones represent isotopes, you say, I don't care how many electrons there are, I'm going to pretend I don't even see that. All I care about is I want to find things where protons are the same but neutrons are different. That's when they're isotopes. Protons are the same but neutrons are different. The number of protons is the same, number of neutrons are different. If that's not true, they are not isotopes that we're talking about here.
Is it possible to have fewer amount of neutrons than?
It is, yeah. So there's, yeah, most atoms have, most nuclei have either the same number of neutrons as they have protons, or more neutrons than protons, but that's not universally true. So when we study fusion in the sun, we'll discover that a step along the way is the production of helium-3, which has 2 protons and 1 neutron. But most atoms have more, either the same or more neutrons than protons, but it's only most atoms. And hydrogen usually just has 1 proton, that's it. Although there's an isotope of hydrogen called deuterium, which has a proton and a neutron. And there's also tritium, which has a proton and 2 neutrons. Tritium is radioactive, it's unstable. Deuterium is stable, but it's rare. But if you make water out of deuterium, if you isolate deuterium and make water out of it, it's called heavy water, because it literally is heavier, because a bucket of it has lots of extra neutrons in it. And so literally you can tell the heavy water was heavier than water that had just ordinary hydrogen. And it's used in nuclear reactors. Okay, yes?
Are we done with this part?
Are we done with that? Any questions about isotopes? Okay, we're done. Yes.
I'll just help me. Maybe you could go over one more time. One of these that says, know the direction and acceleration vector points in uniform circular motion.
Mm-hmm.
I mean, I understand the force of the sun, the gravity, acts like the piece of string for
Right.
the Earth and the planet, so it just circles around
Right.
farther out and then faster when it's closer. So,
So-
is it like a clockwise motion, or?
Well, it doesn't have to be. In fact, think of this. Okay, so if you look down on the north pole of the sun, the Earth is orbiting it, it turns out, let me get this right, counterclockwise. Okay, so if I look down on the sun, so my shoulder is the sun. If you're looking down on the north pole of the sun and the north pole of the Earth, then the Earth is orbiting counterclockwise from that perspective. But now I'm going to keep my arm always spinning the same way. I'm never going to change which way my arm is spinning. Now we're looking down on the south pole. Which way is Earth going around the sun? Clockwise. So clockwise, counterclockwise, it depends on if you're looking down on the north pole or the south pole. So that's not it. The planet could go around the sun in either direction. It doesn't matter as far as that's concerned. And the point is that how do I know that the force is, how do I know that the acceleration is towards the center? Well, you can prove it using calculus, or you can make the little sister argument, where, I said if you have a little sister and swing her around, you need to pull in on her to keep her moving in uniform circular motion, and the acceleration is always in the same direction as the force that causes it. So if I'm pulling in on this little sister to keep her moving around me, then the acceleration I'm giving her also has to be inwards towards me. So inwards force, inwards acceleration for uniform circular motion. A string can give you that inwards force, but so can gravity. Yes?
For Kepler's second law, I can visualize it, I just can't explain it.
So, okay, when you say you can visualize it, do you mean you understand that if I have this ellipse and I'm told it takes the planet the same amount of time to go between 2 points on the ellipse, then the area it sweeps out has to be the same as well? Because that's that. Remember we did that mastering astronomy thing. So let's try to roughly reproduce it here. So, sun. Here's 2 points. Suppose it took some planet 1 month to go between those 2 points. And suppose it also took the planet 1 month to go between these 2 points over here on the missed. Okay, draw the lines and then locate the points. It takes 1 month to go between those 2 points also. So this is 1 month. This is also 1 month. How do those two areas compare to one another? They are the same, right? Equal times means equal areas and vice versa. What if it takes the planet, say, 2 months to go from here to here? What if this is 2 months, compare, I'm gonna do it, bam, okay, and, there, perfect, alright, 2 months to go from there to there. How does this area compare to this area? Yeah, it's not the same, right? So in other words, it's not correct to think the area is always equal. No, it isn't. It can't be that the area is always equal. If that were true, you'd be telling me, the area is always equal, therefore this area is the same as this area. These two areas, all the areas are always equal, so those must be, no. Equal areas if the times are equal. Only if the times are equal. Equal areas in equal times, but only in equal times. So, if the time is twice as big, the area is also twice as big. So if it takes 2 months to go from A to B, and only 1 month to go from C to D, then the A to B swept out area is twice the C to D swept out area. So that's, what you need to understand is that implication, that equal times means equal areas. Now, why is Kepler's second law true? Well, that comes from a detailed study of the physics of the gravitational orbit. In other words, I don't expect you to deeply understand why does Kepler's second law hold. Newton proved it using calculus and his law of gravity, but it should not be obvious to you that equal areas are swept out in equal times. It turns out to be the case for an inverse square law force that is central, it turns out to be the case for any central force, any force that only depends on distance and points towards the center of the or points towards the attracting body, then Kepler's second law holds. But that shouldn't be obvious. So what I want you to understand is what, and not, you don't have to understand exactly why. That's the way it works out, is what it comes down to. So, any other questions about that? Yes?
Kind of going off of that, why is Earth's angular momentum the same when it's closer to the sun as when it's farther?
It turns out, it's because, and again, this is one of these, this is not going to be obvious to you. It turns out that if the torque is 0, then the angular momentum stays the same. Angular momentum is conserved. And it turns out that as long as the force points directly towards the object that's exerting that force, the torque is always 0. And in this context, right here, I'm not even going to try to demonstrate that to you because it's not going to help you on the exam. And so I'm being, normally I love expounding on things like this, but we need to be practical and we're preparing for an exam right now. So unfortunately I'm going to say, it works out that the torque is 0, and that turns out to mean the angular momentum stays constant. It's not obvious. It's just, it's true, it's provable, but it's not obvious. I wouldn't expect you to know why it's true and be able to explain that. Just that it's true. Any other questions about that? Yes?
Would it be wise to memorize what the speed of light is, or will that be something?
No, I would tell you that the speed of light is 2.9979245 times 10 to the 8th meters per second. Right, or 3.00 times 10 to the 8th meters per second. I mean, really, it's not hard to memorize, right? It's 3 times 10 to the 8th meters per second, but I don't expect you to memorize it. Yeah.
Are we going to need to know that in nanometers as well? Do we have to make the conversion?
You should know that a nanometer is 10 to the minus 9 meters. You ought to know. Basically, there's 3 important metric prefixes I'd say first here is kilo. So a kilogram is how many grams? 1,000. Kilo is 1,000. A kilometer is how many meters? 1,000. A kilosecond is how many seconds? 1,000. Because kilo always means 1,000. Right? kilo always means 1,000. So kilo means 1,000. What about centi? A centimeter is 1/100th of a meter, right? There's 100 centimeters in a meter. So a centimeter is 1/100th of a meter. So you should know what centi is. That's 100th of. Pretty much, you should know that a centimeter is 100th of a meter, and a meter is 100 centimeters. And nano is 10 to the minus 9, a billion. So know that a nanometer is 10 to the minus 9 meter. 1/1000th of a meter. Yeah, you should know that, because if you don't know that, it's getting in the way of being able to keep track of what's going on in terms of these units and so forth. So I would want you to know that. Now, if I asked you for the wavelength in nanometers of something, well, you're already kind of good to go, because the formulas we gave already have nanometers built into the units. So there's no conversion to be done. The formulas we're given already are based on, let's get the wavelength in nanometers. So, yes?
And you're giving us the formulas?
I will give you a formula sheet. Your job is to know how to use the formulas. Yeah, you don't have to memorize the formulas, but you should know what the symbols in them mean, and if you're confronted with using a formula, know what to put in for what symbol. Yes?
Are we done with this part?
Maybe. Okay, yes.
So, I'm kind of going off of this question that I asked. So, can you explain how the rocket takes off when it gets launched? Because I think that's my question.
Yeah, so it's a matter of conservation of momentum, which is discussed in the book. It's also, but that comes from Newton's third law. So in other words, suppose that I were on a really slippery pond. No pond is really this slippery, but if I were on a really slippery pond, it's like a pond where the ice is covered with a layer of water, so that here's me trying to make any progress, you know, and then I just fall down. I can't get anywhere, right? Problem is, if I can't get any friction with the pond surface, remember, I cannot move myself. I cannot put a net force on myself, because any part of me that exerts a force on some other part of me, well, that other part exerts an equal and opposite force, so the net force on me is zero. Those two forces cancel. The only way I can move my center of mass is to get something else to exert a force on me. So I can move across this floor by getting the floor to exert a force on me. If I were on a slippery pond, a super slippery pond, I couldn't get the pond to put a force on me, I'd be stuck. But there's a way I could get myself to move across the pond. I take off my jacket and I whip my jacket. Alright? So now, as I'm throwing my jacket, am I exerting a force on my jacket? Yes. Is my jacket exerting a force on my hand backwards? Yes, it is. So what happens is that as I whip my jacket, now I let go of it. It's not part of me anymore. And conveniently, the fact that I had to push on it to make it fly this way means it had to push on me to make me start flying this way. And on this perfectly frictionless pond, I'll just keep slowly sliding towards the shore and say, I made it. That's what a rocket does, only what's happening is the rocket is pushing on its own exhaust gases, which makes them blast out the back, but if it's pushing on its exhaust gases, they're pushing on the rocket in the other direction, and so the rocket gets momentum transferred opposite the direction that the gases do, and that's how rockets fly. You can fire a rocket in outer space. It's not the rocket gases pushing off on anything other than the rocket itself that is causing the rocket to move. And that's what happens when a rocket launches too. It's pushing off against its own gases. The ground is not a part of this, the air is not a part of this, it's just the gas. The rocket and the gases are pushing on one another in opposite directions. Yes?
Can you explain why Newton's first law is 1907?
Like why is Newton's So it's actually the other way around. It's not that Newton's first law is explaining Newton's second law. It's that Newton's first law is a consequence of Newton's second law. That if all you knew was Newton's second law, you could get Newton's first law from it. You don't need a separate Newton's first law. And that's because Newton's second law, well, that says acceleration is force divided by mass. It's actually got warm enough in here. I don't. So now I take it off and I'm cold. I put it on and I'm hot. Okay, I'll just be cold for a while. Okay, so acceleration is force divided by mass, right? If force equals 0, then A equals 0, 2, right? If the acceleration is the force divided by the mass, but the force is 0, then the acceleration is 0, but acceleration is rate of change of velocity. So the velocity is not changing. If there's no acceleration, by definition, that means the velocity is not changing. But remember, velocity is the combination of speed and direction. If the velocity is not changing, the speed is not changing, the direction is not changing. So the speed is not changing. The direction is not changing. If I'm moving such that my speed is not changing, and my direction I'm moving in is not changing, I am moving in what way? I am moving in a what, blah, 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 in a... So, if my speed isn't changing and my direction isn't changing, I am moving in a straight line at constant speed. I'm moving in a straight line at constant speed. Newton's first law says, if there's no force, the object moves in a straight line at constant speed. So that's the point. In other words, Newton's second law, where you plug in no force, says the object moves in a straight line at constant speed. That is Newton's first law. So Newton's first law is implicitly contained in Newton's second law by plugging in that the force is equal to 0. That's what we mean by that. Is that Newton stated 2 laws when he really only had 1, because the first one was really just the force equals 0 special case of the second law. Which wasn't really cheating, because the point was people didn't really realize that you don't need people often didn't realize before Newton and Galileo really that you don't need a force just to keep something moving. And so he felt the need to explicitly say the first law, because he was basically saying, people, you don't need a force to keep something moving. Even though it's really implicitly in the second law, he just wanted to emphasize that fact by stating his first law. Yes?
How do we calculate the wavelength or frequency of a wave when given its energy?
Yeah, so then we use the formula, which says that, can I erase this part? Because I want to write on it again, because the people at home are looking at this part right here. So, yes, okay, here it goes, alrighty. Okay, so there's a formula that says that the wavelength of a photon is 1240 electron volt nanometers divided by the energy of the photon, or flip it around, the energy of the photon is 1240 electron volt nanometers divided by the wavelength of the photon. So all you do is plug the wavelength in nanometers if you're trying to find the energy, and then those nanometers will cancel. Or you find, if you know the energy of the photon, which would be given in electron volts, you plug that into this formula, and then the electron volts cancel, and you just left with nanometers after you divide. So that's really all there is to it, is you just plug either the energy into this formula, or you plug the wavelength into this formula, and let the calculator tell you the answer. Yes. At the front of the room, I'll bring them in. Yeah, no, so I just bring them in front of the room, and then you prick your finger and sign in blood, and then we're good to go. Yes?
Can you do an example problem, like 4.5 mass spectrometry, which would be like, how do you find the mass of, say, like the Earth from knowing the period and the time?
Knowing the period and the time and all that business.
Yeah.
Yeah, so of course the difficulty is making up numbers, to go with this. So, okay. Basically, I'm not going to ask you to do that on this particular example. So, I could, but let's do something else instead. Yeah, I know it's very disappointing. I've got some tissues if you need them. But, yeah, okay. Yes.
What concepts in the law of gravity or gravitation are we going to need?
Look at your study guide, and that tells you what I want you to know, basically. Yes?
Can we ask you if there's any quantitative problems that we should focus on, or just all of them?
No, you should not one where you find the mass of a planet given its orbital period in years, or so not that, but just look at the mass ring astronomy stuff and be ready, unless it's one that's about finding the mass of Titan from its orbital period around Saturn or something like that. But other than that, no, I want you to just kind of be ready for any of those kind of things. Yes.
Can you do an example using the Stefan-Boltzmann law?
Sure. Here's the thing too. So Stefan-Boltzmann law is this one that says that flux is sigma t to the fourth. Okay. Now, sigma is this number 5.67 times 10 to the minus 8. Blah blah blah. I'm not particularly interested in a question that would say like. The temperature of this star is 4,700 Kelvin. How many watts per square meter are emitted from each square meter of its surface? In that case, what you would do is you would take 5.67 times 10 to the minus 8 and multiply it by 4,700 to the fourth power. But what I'm really interested in your being able to do and to understand is the implications of it being the temperature to the fourth power. Meaning, I could say something like, star A has a temperature, a surface temperature of 5,000 Kelvin. Star A, 5,000 Kelvin. Star B, temperature is 15,000 Kelvin. How many times bigger is the flux from star B, that's going to be the bigger one, compared to the flux from star A? How would you do that? How would I figure out how many times bigger is the flux from star B compared to the flux from star A? Well, how many times bigger is star B's temperature than star A's temperature? 3 times bigger, right? So what we say is, well, star B is 3 times hotter than star A. Just 15,000 divided by 5,000 is 3. So you just divide the temperatures. Star B is 3 times hotter than star A. So its flux is how many times bigger? Don't tell me the number, tell me how to get the number.
3 to the 4th.
3 to the 4th power. That 4th power there says whatever factor I multiply by the temperature, by, I have to do that to the 4th power to see what I did to the flux. So its flux is 3 to the 4th power times bigger. And what is 3 to the 4th power? Well, you can key it on your calculator, or you can say, well, 3 to the 4th power is 3 multiplied by itself 4 times. Or in other words, it's 3 times 3 times 3 times 3. But 3 times 3 is 9 times 9. 9 times 9 is 81. So star B's flux is 81 times bigger than star A's. And that's really what I'm interested in, is being able to understand the significance of it going like the 4th power, depending on the 4th power, to understand that, I just do a little bit to the temperature. I make it 3 times bigger. Holy crap, the flux is 81 times bigger. Same deal with the light bulb. Remember I was saying, we didn't measure the temperature, but the thing got obnoxiously bright. Its brightness increased a lot more than its temperature did, because its brightness depends on the 4th power of the temperature. So it rises a lot more than the temperature does, is the idea. Yes?
So by saying the 3 to the 4th power equals 81, is that showing why and not just
It's showing that you understand that.
not what happens, but why it happens?
So, well, again, why is it F equals sigma t to the 4th power? Well, the derivation of that comes from doing thermodynamics calculations. So it's not obvious. It shouldn't be obvious to you that the flux is sigma t to the 4th power. That's a subtle thing to prove in a junior, senior level physics class. So here we're just like, you're trusting the people that did this to not lie to you, and they're not, okay? But what I want you to do, in other words, is to understand that the fact that the temperature to the 4th power means it's really sensitive to the temperature change, and to be able to do this much quantitative calculation. If I know how many times bigger the temperature got, I can tell you how many times bigger the flux got by raising that to the 4th power. So that's really what it comes down to. If it got 10 times hotter, if star B's temperature was 50,000 Kelvin, the flux would be how many times bigger? How many times hotter is 50,000 than 5,000? 10 times bigger. So the flux is 10 to the 4th times bigger. 10 to the 4th is also popularly known as 10,000. So raise the temperature by a factor of 10, the flux goes up by a factor of 10,000. Is the idea. Yes? Yeah, any other questions about that?
If please do an example of I'm going to slaughter name.
Wien's law. Yeah,
Oh,
Wien's
like
law.
Vienna.
Yeah, Vienna, right, yes. Yeah, good phone in Wien. So, so Wien's law. So, do an example of that one. Yeah, okay. So one example of Wien's law is like mastering astronomy tutorial, where you realize, if it's a hotter star, I need to make the peak at a shorter wavelength. Right, so qualitatively, Wien's law says hotter star peaks at a shorter wavelength.
Yeah.
And then quantitatively, right? Who's calling me? That's funny. I don't think this has a microphone. Incoming phone call from. Okay, I don't know who that is. 440. Is that no?
Is that like Cleveland?
Was that? Is it? Now Kyle had called before. It was back there. Let me just. I said slobbering. Let me just see if that's Kyle, because I think this was 440, and I'll be right back. Gmail, you set up Google Hangouts to take phone calls. So if people call my cell phone, I can answer it on my laptop. Anyway, I know, yeah, Apple thinks they're so smart, but it's been available with Android for a long time. But anyway, anyway, where were we? What were we even talking about? Bean's law, yeah, right. So, a quantitative example with Bean's law would be, for example, sun. Temperature of its surface is right around 5,800 Kelvin. At what wavelength does sun emit most strongly? Yeah. By the way, if you ever heard one about, I know I'm right. That's why my mom calls me son. Anyway, so at what wavelength does the sun emit most strongly? Using Bean's law. So, using Bean's law here, if we solve for lambda peak, in other words, we flip them over. Lambda peak is that number divided by the temperature. Lambda peak is 2.9 times 10 to the 6th power nanometer Kelvin divided by that temperature of 5,800 Kelvin. Well, if you plug it in, you find that 2.9 times 10 to the 6th divided by 5,800 is in fact 500. So the answer is 500 nanometers. The sun's spectrum peaks at 500 nanometers. That's where it emits most strongly. Is 500 nanometers visible to humans? Yes. It sure is. It sure is. As I think I said in class, it's a puky yellowish-green color. And it is. It's not very attractive to my eyes. But in any case, that's where the sun emits most strongly. It doesn't mean the sun is that color, because it emits other wavelengths too that blend together to give it a whitish appearance to our eyes. That's Bean's law in action. If I know the temperature of something, I can tell what wavelength it will emit most strongly just by plugging into the formula. And you should understand the idea that, so what this is saying here, if I write it in terms of lambda peak is number over temperature, 2.9 times 10 to the 6th nanometer Kelvin divided by the temperature. If T gets bigger, what happens to lambda? Gets smaller, right? If you divide by a bigger number, the result is a smaller value. So built into this formula is the idea that if I make the temperature bigger, the lambda peak gets smaller. 3,000 Kelvin, lambda peak is here. 5,800 Kelvin, lambda peak got smaller. 15,000 Kelvin, lambda peak got smaller still. That is, the temperature increases, the wavelength where it peaks decreases, gets towards smaller wavelengths. Which kind of makes some intuitive sense, because shorter wavelengths, are the photons more energetic or less energetic? More energetic. Shorter wavelengths are higher energy photons. So this is saying a hotter object likes to give off more energetic photons. A hotter object peaks at a shorter wavelength, it's giving off more energetic photons as a result of it. Kind of makes sense. A hotter star likes to give off more energetic photons, so to speak, than a cooler star does. So, yes?
How big are you going to do about sig figs?
Oh, I'm not, for these purposes. Yeah, I'm not particular about them. I'm sorry, but I'm just not going to be particular about them. I might feel the need to make a snide comment if you give me 17 sig figs and I'm like, you don't really know that to a precision of parts in a quintillion or whatever. But you won't get points off. You'll just maybe get a snide comment from if you overdo it with the sig figs. Yes. Yes?
Can you explain mass energy?
Yeah, so, yes, and it's not going to be on the exam.
Okay.
But it's the idea that E equals mc squared, yeah. So we're definitely going to do that, but we're going to do it later. When we talk about how the sun shines, we'll bring that in. but I've decided to wait until we talk about how the sun shines rather than do it now and then have to do it again when we talk about how the sun shines. Yeah, but it's E equals mc squared. It's Einstein's famous formula that's involved with that. Yes?
Kind of going on that, so we need to know then how to calculate kinetic and potential energy?
Nope. Do know that kinetic energy is energy of motion, but I'm not making you use like kinetic energy is 1/2 mv squared. I'm not doing that. Yes?
Bouncing off of that, does that mean that we need to understand that kinetic energy is what changes the temperature?
Well, you should understand, yes, that what distinguishes a hotter object from the same object at a smaller temperature is, well, in general, hotter objects have higher average kinetic energy of their particles. So this room, if I turn on the heater, the air molecules are moving faster. That's what makes it warmer, is the air molecules are moving faster. Temperature is a measure of the average kinetic energy of the particles of the substance.
Do we need to know how to, because it's in the book, but you didn't know mastering astronomy, how to calculate the Doppler shift?
Yeah, we didn't. So for these purposes, later on I'll have you calculating, but for now, I just want you to understand that blue shift means moving towards, red shift means moving away. The bigger the blue shift, the faster moving towards. The bigger the red shift, the faster moving away. When we talk about using Doppler shift to measure stars' masses, then you'll have mastering astronomy where you have to apply that formula, but I haven't done that yet. Now, again, I choose to put it directly in the context of where we're actually going to use it for something. So I'll wait until we're actually using it to measure star masses. Yes?
Are we,
I think so, yeah, because I said, no, you don't have to use the
That's
formula.
true.
So
That's true.
can you explain how we don't use the formula? Right, yeah.
But there is, I don't know if this is something that will be on the exam or not, but there's a question on mastering astronomy where it has like 3 slides, where one's a straight slide, one's a concave, one's a convex. And this is, why is the speed at the bottom of the slide all the same?
Yeah, that's an energy conservation thing, and that's also not going to show up. Yeah, it's not an ironclad guarantee, but it's, well, okay. I mean, that could have, because it was in mastering astronomy, but yeah, okay. So I'll just stop there. Yeah, that won't happen. Yeah, that's yes.
There's a part in the study guide, I mean, obviously, once I start saying it, you'll pick up on it. Know why every element has its own unique set of spectral lines, blah, blah, blah.
Yeah.
So, could you kind of explain,
Like what? Yeah. So what? Yeah. So the fact that every element has its own unique set of spectral lines ties directly with the fact that every element has its own unique set of allowed energies for the electrons. So in other words, here are the energies for hydrogen, and the spectral lines of hydrogen correspond to wavelengths that are just enough to make electrons jump between energy levels. Right? So in other words, hydrogen can absorb 10.2 electron volt photons because they have just the right amount of energy to make it go from the first level to the second level. Other atoms have different spacings of these rungs. Other atoms have different allowed energy levels for the electrons, which means different energies of photons are going to be needed to cause transitions in those atoms. So that's why they all have different spectral